But I think one of the great things about material science is that when you put your effort into developing new kinds of compounds for a particular application, those same materials can be used for many other applications as well.
Hello, everyone. My name is Manish Chowalla. I'm the editor-in-chief of MRS Energy and Sustainability. And today I've got Professor Robert Hoye from the University of Oxford, who recently published a very nice review paper in the journal.
Very, very pleased to be here and very honored to have contributed to your journal.
Your review paper was on bismuth-based X-ray detectors. So can you just take us through how you discovered these materials and how you discovered that they are good candidates for X-ray detection?
I suppose we take a step back to the motivation behind this work on discovering new materials. It all comes down to making better detectors for things like medical imaging in particular, because when people take something like a CT scan or a mammography image, there's quite a high dose rate X-rays which are used, and several orders of magnitude dose rate above background levels. So there's a risk of causing cancer from taking these medical imaging scans. And that's all down to the capabilities of the detector which are being used. And with the lead halo perovskites, research that started over a decade ago into solar cells, but also people began looking into them for X-ray detectors. And because of the capability of these materials, they've significantly lowered the dose rate required for X-ray medical imaging. But of course, we all know that with lead halo perovskites, lead is an intrinsic part of the material itself. These compounds have limited stability in air. They require quite a lot of encapsulation in order to preserve their properties over time. So this is what motivates discovering alternative kinds of materials. But I think one of the great things about material science is that when you put your effort into developing new kinds of compounds for a particular application, those same materials can be used for many other applications as well. And with these bismuth-based materials, things like double perovskites, things or the triple perovskites, as well as non-perovskite compounds, they have a lot of the right properties for X-ray detector applications. So in particular, that's the high effective atomic number. So if you think about bismuth, this is just to the right of lead on the periodic table. So it's the heaviest element that's not radioactive. So that is conducive towards strongly attenuating ionizing radiation. If you combine this with something like iodine, for example, you make methylammonium bismuth iodide or bismuth oxyiodide, you have a very large effective Z number. So that means that the amount of material you need to attenuate this ionizing radiation is reduced. Also, these bismuth-based materials, unlike lead halo perovskites, they're non-toxic. There's no evidence for toxicity in these compounds. So, for example, people use bismuth oxychloride for cosmetics. So that addresses important limitation with these lead halo perovskites. And in addition, a lot of these bismuth-based compounds that people have been exploring, that we have been exploring, have been shown to be stable in air without encapsulation. And that is quite promising in terms of the long-term durability of these devices.
It definitely sounds like an exciting material system and field. These bismuth-based perovskites come in different flavors in terms of their structure. They can be 0D, 1D, 2D, and even 3D. So can you just say something about the advantages and disadvantages of changing the dimensionality of these materials and how that can be used to optimize performance for X-ray detection and maybe other applications?
Yeah. I mean, as a material scientist, the ability to tune the dimensionality of such a wide range is really exciting for me, because there's so much variability and that we can tune these properties over. So I mean, absolutely, in terms of the dimensionality, that is very important for many different reasons. I mean, the advantage from reducing the dimensionality is that you can lower the dark current, and that is very important when it comes to reducing the detection limit. So going from 5,500 nanograys per second, if you lower the dark current by a lot, by increasing the resistivity, you can lower the detection limit down to 10 nanograys per second. So if you have a detector that only requires, orders of magnitude lower dose rates than what's currently needed, then this can make medical imaging a lot safer for the patient. So reducing dimensionality is important in that respect by increasing the resistivity, lower the dark current. The disadvantage that comes from lowering dimensionality comes when it comes from the mobility lifetime product, because for X-ray detector to be efficient, to have high sensitivity, the mutile product needs to be high enough that you have a high enough drift length, which is comparable to the length scale that you need in order to attenuate sufficient radiation. As I mentioned, we can tune the dimensionality among this family of materials. And one of the exciting classes of compounds we've recently been looking at is bismuth oxyiodide. So this bismuth oxyiodide is structurally and electronically two-dimensional, but within these layers, each slab is relatively thick. And what we've been quite pleased to find is that this material does not have chiral localization, so we can actually get very large mobility lifetime products. So you're absolutely right, dimensionality plays a very big role, and it is excellent that within this class of compounds, we can tune this over a large range to tune and optimize the properties, charge carrier transport properties of these materials.
So have you been looking at artificial intelligence and machine learning as a way to find optimal properties or synthesis conditions or sort of relationships between structure and property to optimize the performance of these materials in X-ray detection and other applications?
I certainly think machine learning can be very helpful, and especially when it comes to looking at the broad materials processing space. I mean, I suppose it takes a very skilled material scientist to use their intuition to navigate their way through this treacherous space and work out the best way to optimize the processing of these materials. I think AI can certainly help in speeding that up.
What are the commercialization prospects for this technology? Are you looking to commercialize your discovery?
Absolutely. We are very excited about doing this. And I mean, it's not just us who are working on this. There's many other groups in the world working on this as well, which is great for the community. So in terms of the areas in which these are being commercialized, one is single crystal materials for photon counting detection. So this is the latest technology that's being used for CT scanners. You also use for advanced spectroscopy as well. And so there you have to have single crystals with very high mobility that allows you to extract all the photo-generated charge carriers very efficiently from your material. The other end of the scale is sort of lower end, but still important medical imaging application, things like mammography, device inspection, quality control. And there, you don't necessarily need a single crystal. You can use a flat panel X-ray imager made from polycrystalline material. So with bismuth-based compounds, as I mentioned, the advantages of these materials and the importance is the fact that they're made of non-toxic elements. And I think that is important since, if we compare these with solar cells, we have a lot more material here because we need to have much thicker materials, either thick films, micron thick films, or single crystals for these to work for attenuating the radiation of this. So if you make that all from lead, we have to consider where that will end up in terms of the life cycle of these devices. So having non-toxic bismuth-based elements is an advantage in that respect. And plus the fact that these are stable without having to have encapsulation. That's also a big advantage.